So next is Yanqin Wu. She's an associate professor here in Toronto.
I just want to answer your question yesterday. You were asking what predictions in planet formation has ever been proven true. Is that the question? Okay. Actually, I think this plot probably shows one of the predictions fares well, remarkably well. This is the Kepler. So down here, this is mass of planets. I see planet mass these days. But 3 orders of magnitudes in range, so we know a huge planet in range about planets. And the green ones, these low mass ones, what Yoram's been talking about, Kepler planets. And they're sitting pretty close to star disk orbital periods. And I think one of the predictions of planet formation, conventional planet formation theory, was saying that you either get low mass planets or you get gas giants. It's very hard to have planets in between here because planets which have enough mass, which just undergo runaway gas accretion and pass through distribution very rapidly and become gas giants. That looks good. Just don't look at this part. Does that convince you that's one good prediction that works out?
First, I'd like to know if the orange ones include ground-based transit planets.
Yes. So the yellow ones or the orange ones are the radial velocity determined masses of ground-based transit planets.
Because there's an obvious selection effect that tends to increase the number of short-period large planets, which is that a lot of them have been discovered by transits from the ground, and you can only discover them if they're large and short period.
Well, I guess what I'm talking about is that at the same period, and you can look at the masses.
Right. So there's a whole at a given period, you can discover a whole bunch of big ones even in the ground, and then Kepler discovers a whole bunch of little ones.
And Kepler has no trouble detecting intermediate, as you can see.
Yeah, but it's just saying that there's a population that has a gradient with the number per log mass increases as you go down, and then you get a big extra bump from the ground-based transits.
So the fair example is take Kepler alone, because Kepler has no such selection effect. And I think it's Proton, but in Kepler, in sizes, there is a continuum. In the sense that above Neptune size is a continuum of transiting object. There's no tie-up in sizes. But we're claiming there's a tie-up in mass, meaning, there's continuum of planets up here, as many here as up there, which doesn't tell you anything. But what could tell you is that once you determine masses, you realize there's a big gap between planets which are less than 20 Earth masses, that's what we call a Kepler planet, and giant planets, which is 200 Earth masses.
Maybe, but we don't have the masses.
Some. Okay. All right. So let me talk about this problem: stability of LargeN planetary system. So it's actually mostly the research done by two of my brilliant undergraduate students here in Toronto. So I didn't do any of the research. They just keep on working when I'm teaching. Works out pretty well. So by LargeN, okay, there are lots of cluster people and galaxy people here. So when I say LargeN, what does it mean? N means LargeN means 10. In fact, what I want to quantify LargeN being that what we care about in planetary system, because planetary system is probably flat and going in 7 major axes in decades, what we really care about is how many planets there are within one 7 major axis decade. We don't care about the next decade or third decade. Normally we can't detect them at the moment, but also they're not dynamically important if they're in a different 7 major axis decade than the one we care about. Okay? And for the one we care about, by LargeN, I meant systems which have about 10 planets squeezed in one decade. Okay? And in contrast, the solar system have about 5 planets species in 1 decade. I didn't know this, but Googling helped. Kepler in 1611 asked this question: that what's the maximally packed crate of oranges can be? What's the maximum way you can pack oranges? In fact, I don't know the oranges like that. Probably pack oranges. Sorry. How do you maximally pack spherical objects into a given volume? Okay, that's his question he asked. And it's kind of funny that he didn't ask the question about planets. So what we're going to ask today is the question. Yep.
He did.
He did.
You see this picture when he tried to fit all of the planets into geometric shapes, with tetrahedrons, cube, and all of that. And he was not trying to do a boson. He was trying to use this geometric shape to see the maximum number of planets.
What's the
You see these pictures where Kepler is looking at fitting in tetrahedrons,
Yep.
cubes, and what do you call it? Whatever.
I can take all the number of regular solid regulars equal to
Solid,
the
yeah.
number of.
That's right. And he was
Unknown
making
planets.
attempt. He was making
But what's
attempts
the
to do
volume of the
that.
planet?
Filling the
Dash
volume.
one inside each other.
Oh, I see. I see.
This was-
Inside of each other.
This was Kepler's first law. That is, he had 3 laws, and one of them was really stupid, and the other 2 were the ones that we remember. But the first one was the one about this radial spacing of the
Yeah.
planets.
With all the geometric figures.
So is it any better than Bode's law?
No, it was a theoretical prediction.
Sorry?
It was a theoretical prediction, not an observational fit.
Was a better theory because this is actually a complicated mathematical problem. It's a real hard way. Okay. All right. So what I want to do is today is, given the Kepler data, and given you can do computer simulation these days to as long as you want, let's try to answer that question at least partially. Okay. This is again showing the same plot like Jordan showed you earlier about Kepler multiple systems. I'll just keep the number up there. This is updated yesterday. And Euron's plot is from a year ago, so it changed. Number of multiples doubled. For example, in 5 planets or something, where you see 5 trending better. I think his plot is only up here, and now it's up to here. So numbers are increasing. But I want to use this couple of plots to show you the next few slides. The point I want to make is that those large N systems do exist in nature. Okay, so this is the rough statistics today from Kepler systems. This number looks so innocent, but it takes a lot of work to get out. Roughly, if you look at average, if you take the total number of planets and divide the total number of stars in the galaxy, the number ratio is about 0.8 within our observable sphere. That doesn't mean every star has pretty much 1 planet, because many stars are actually way more fertile. Our solar system only have 8. And some of these Kepler systems could easily have 20 or 30 or even 40, who knows? So many are very fertile, so this is not even a democratically distributed, but it turns out that about 10% of all stars in the Milky Way have large N planetary system. 10% is a bit of a guess at the moment, we're trying to quantify it, but large N meaning fitting 10 planets within 1 decade, so 7 major axes. This is one example. This is the Kepler 11 system that you showed before. It's got star in the middle and then all the way from 0.09 AU, which is the closest one that we can see, to the furthest one that actually transit. This is only a factor of 5 with 7 major axes, but nature managed to squeeze in 6 planets already. Not only that, if you look at the period ratio of these planets, so this is the second to the first, it's 1.26 and so on, there's a period ratio. You don't need to take too much intelligence to say, well, I can take another planet here, because this period ratio is too large. So it's probably more like 7 planets in this system within that factor of 5 with 7 major axes. And what we've been showing is that this, so there's probably another one there, we just happen to be the wrong orientation. What we've been able to show is that Kepler systems don't stop at these distances. They probably keep on going for as far as Kepler mission are able to observe. In fact,
did you see an evidence for that missing planet on PTV?
no, it's no. Part of the reason is because, sorry?
There's no
Go ahead. I want to ask something.
Part of the reason is because, as Jerome was saying, you can only see large CPV signals if the two planets happen to be close enough to a first order resonances. And some of it's made, some of it's not.
But that one wouldn't?
But not seeing TDV signal does not exclude it's not there. Because it may not be in the resonance. So I have no evidence.
So in the previous plot where you had the numbers, there were error bars. Are these supposed to correct for some observational bias?
No.
What are the
It's
error bars?
just
Just crossover. Because it looks like there's a lack of 6 and 7 planet systems compared to the others. If you just draw a line and extrapolate with them.
Well, this depends, it depends on the relative orientation of the planetary systems, and depends on the spacing between planets and so on. So we don't really have good theoretical picture of how big these flows are. This falling off tells you something, but I'm
I
not.
think Scott,
Yeah.
well, maybe Scott can tell me 6 and 7 are consistent with 1, 2, 3, 4, 5.
Well, if you just look at the error bars, yes.
Okay. Looks like we're missing a few.
What I do agree with you, which is what Norm is bringing out this point, that when one does modeling, assuming everybody is this kind of system and try to extrapolate back at how many single systems there should be, usually you get numbers around here. So there are too many singles for some reason. Those are details. So for galaxy people, you don't have to worry about those. All I want to convince you is that LargeN system exists, not only because this system has already probably 6 or 7 planets, but this system, people are extending ours, because as far as we can see, we've done some modeling on how the planet number depends on periods, orbital periods. It's roughly, we can fit it with a single power law. Number of planets goes around logarithmic period, and that power law number is 0. That means every logarithmic period decade is about the same number of planets. So this elevator of planets just keeps on going as far as we can tell. We can see. I wouldn't be surprised if this keeps on going to 108 years. Okay. All right. So what do we do with these LargeN systems? Dump it to the computer. Use this fancy, powerful mechanism called symplectic integrator that Scott's going to talk about tomorrow. In this case, if you did this exercise, take the Kepler 11 system, 6-planet system, integrate it for 250 million years. Okay. Sounds short to you, 250 million years, but that's 10 to the 10 dynamical time scale. That's the end of our computer capability at 5 billion years after the burst of the sun. What do we do then is that we do a technique called Fourier analysis of the orbits. So Scott also mentioned this thing called Poincare variables, which is kind of action angle variables, which often happen in galactic dynamics. We take this Poincare variable and take its time spectra, time power spectra, and this is what's shown here. For example, this is the Kepler 11 system itself, the one that's determined observationally, and assuming there's no eccentricity in the system, no inclination, so very, very close system. And you can see the power spectrum of that 250 million years integration shows 6 beautifully sharp delta pointed peaks. Those are called the secular eigenfrequencies and so on. This is a very stable system. Kepler 11, as the parameter given, are very, very stable. But if you raise the eccentricity a little bit, it becomes very chaotic, and then it can actually disrupt in a very short amount of time. So what I want to show with this graph is saying that such a frequency analysis of the Poincare variable can give you an indication for stability. And then we went on to do more. We take those frequency analysis. So this one red line here, 0 here, means planet C, the second planet, let's say, is sitting right at where we observed from today. And then we just do integration of that system and take a Fourier transform integration. Fourier transform is very, very black, except at certain frequencies, very, very black certain frequency. That's correspond to the very sharp secular peaks. Okay? So the current system is very stable. It's right at the black region, very stable region of phase space. But if you turn the planet C around, just shuffle it a little bit around by 3% one way, 3% the other way, you see these white bands? Those are the chaotic or unstable frequency map I showed you earlier. So what it says is that the planet C was placed in some position and is sandwiched by unstable bands, even a couple percent changes of its position would have destabilized its whole system. This is another exercise. You can play with computer, basically anything you want. So what do we do with such a frequency map? I think we were trying to use this kind of hypothetical simulation, to shift C around or shift B around, any of the planets shift them around, and then see how many instability you encounter. Is there any kind of uncrossable instability? For example, if C is not lying in this position, the current position, but has been migrated. Darwin's favorite migration mechanism, and let's say going down in frequency in position domain or going up in position domain, it's going to encounter some of these unstable bands. How is it going to survive? The system is going to survive through that migration history. All the things we can study using this kind of frequency map. So if you're interested, I can talk to you about that. But what I would like to focus in the remainder of my talk was this question: what gives rise to any of these instabilities that we see in this map? Actually, I'm not going to focus on that because that's actually a student project. Let me focus on something related to that. Okay, that was Kepler 11, this textbook example of a LargeN planetary system. We don't have to be restricted to just one system. Let's look at lots of systems. So we generated lots of Kepler 11-like systems, just changing the spacing between planets, masses, and so on. And we just take one index, okay? Just using one index to quantify, to characterize each one of these systems. And that index is here, this K thing. That's basically spacing between planets. So let's imagine a planetary system. They all have the masses like Kepler planets. Jerome has discussed how those masses are determined. But let's say they all have masses between few tens of Earth masses, few Earth masses, few tens of Earth masses. But then let them all spaced by a certain number of Q radii apart from each other. Okay, so 9 here would mean every planet is pretty much spaced by 9 Q radii apart from each other. And then just integrate it in the computer and see whether that system is going to survive. Okay, let's focus on one curve. Let's say this is 10 to the 6-year curve. Okay? Well, this curve is showing that if every system, let's say, starts at 8 Q radii apart, by the time you integrate for a million years, which really should be short million years, okay? About 50% of them have been disrupted. There's some probability of disruption. What's the probability? Came about, I have some guess, but I'm not sure. Okay? But then if you have a spacing of 11 Q radii, you see that those systems can easily survive to 10 to the 7, 10 to the 8, even a half, 10 to the 9 years. Okay? So this tells you that this K is a very good indicator of stability. We just need to know what K those systems have, if I can sort of tell you how stable it's going to remain for. So we were only able to